So image reconstruction in PET, we obviously have a radio tracer distribution inside a PET scanner field of view. Here is a PET MR scanner, and we collect maybe up to 1,000 such sinograms in this sort of vector M that I'm calling it here. And reconstruction is all about, conventionally speaking, using some kind of algorithm like filtered back projection or ordered subsets, EM, to reconstruct some vector which is a representation of the radio tracer distribution inside the PET scanner field of view. Okay, so let's take a closer look at what we're doing when we reconstruct. So we have our collection of sinograms, whether it's SPECT, whether it's PET. Then we conventionally write some algorithm to do the reconstruction. And what we're doing there then is taking input data, we're running it through a sequence of operations, in other words, an algorithm or a program, some code, in order to deliver some output parameters, which would be a reconstructed image. So here I've got a very crude starting example of how code might look for doing filtered back projection. Anyway, it's just a sequence of operations. That's what I want to convey here. So input goes into a cascade of operations that we write with our known models to deliver some output. So what about deep learning? How does that fit into this kind of context of input, output, and code? Well, with deep learning, instead, typically what is done with supervised learning is that we're now supplying a known input and a known output. So these are kind of pairs for supervised learning. And instead now, what we're trying to do is find a parameterization of a general code that gets us from that input to that particular output. And you might ask the question, well, why do that with reconstruction? Because as we've seen up here, we know how to code up filtered back projection. We'd even know how to do Poisson log likelihood with MLEM and so on. Well, why look at deep learning? Well, the point is that there can be tasks that are actually a bit too difficult for us to write the code for. So if this were a classification task of taking an input image here rather than a sinogram, if we had an input image and if the output from our code was meant to be a classification, is this a healthy or unhealthy brain, then writing the code for that would involve a lot of very difficult handcrafted features, not at all obvious how we would do it. And of course that's where deep learning comes into the rescue by learning effectively a cascade, a sequence of operations on this in order to learn particular features via convolutional encoding to deliver some features that allow us to very easily do some kind of linear operator on those in order to deliver some prediction of the output. And the point is that we supply many known inputs, many known outputs, and therefore we learn what the code is that gets us from the input to the output. So that's normally why deep learning would be looked at. But what we're talking about in this talk is kind of going back to the case where arguably we already knew how to solve the problem. We didn't need deep learning to do reconstruction. But I'm just pointing out here, and I'll develop this a bit more, that even when we know how to, or rather we claim to know how to do the input to output mapping like here, we can still use deep learning to, if you like, pretend we don't know, or rather to acknowledge that there are parts of the process that we don't know. So here's a particular architecture which I won't go into in this talk, where the sinograms would be encoded into some latent space and then decoded back out to some image. And this is largely a data-driven learning of the code that would do something like a filtered back projection reconstruction, but of course hopefully better quality in the case of deep learning. Okay, so I just want to convey, therefore, this kind of introductory perspective that there are effectively two ends of the spectrum that we're dealing with. The top case here is, if you like, the mathematics, the statistics, the physics, where we hardwire that into our predetermined a priori code, where we're claiming we know how to get sinograms and how to produce images by whatever algorithm it is that we claim to know so well. And at the other end of the spectrum, this kind of deep PET architecture, where really there's still what we call an inductive prior here. There's still a kind of a structure in the code here, but it's largely very open-ended. And instead, therefore, instead of maths, stats, and physics, instead we use training pair examples to learn what that code is. And this is like the data-driven end of the spectrum. So what you can see that I'm showing here is that we've got one end of the spectrum being our claim of exact modeling knowledge, maths, stats, and physics, and the other end of the spectrum where we're saying, no, we don't know anything at all, just give us the data and let's learn the mapping. And what I want to convey here, because this is clearly what I see as the future use of AI, deep learning, machine learning, is that we're always going to ultimately be seeking some kind of balance between these two very extreme ends of the spectrum. Conventionally, we've been here. Recently, we've been encouraged to go to this end of the spectrum, but in reality, we're always going to be doing some kind of balancing act between known models and then use of data to fill in gaps in our knowledge. And just to point out also the kind of pros and cons of these two ends of the spectrum, with the case where we write the code, we claim we know what we're doing, these kinds of models will, so to speak, generalize very well. They will work outside distribution. And the whole point of a distribution is when we're talking about data. The point is here we're not using data, so there's kind of no risk. We're not using training data. There's no risk of kind of going outside the domain of your training data. And so there's no risk of that with these approaches. Whereas if we lean entirely on the data, then we can actually get really impressive performance in reconstruction, but we have to rely on our input data, the test time, unseen data being within the distribution. Otherwise, when we go outside distribution, we suddenly run into all kinds of possible problems. So I just want to emphasize this balance between our knowledge and the data. Okay, so let's take a look at some examples, just a very limited sample of reconstruction methods and where they sit on this spectrum. So we've got the kind of the pure modeling end of the spectrum. This is our conventional filtered back projection, MLEM, ordered subsets EM, regularized reconstruction. They are examples of where we do not use any training data. We claim that we know it all. And of course, you can already see tell by my language that I'm not quite believing that that's the case. And so I'm suggesting we do need to move away from that end of the spectrum. But then the other end of the spectrum, we have architectures like DeepPet or AutoMap in MR, where really they've just gone too far, so dependent on the data, the training data, that we're really at risk when we go outside the distribution of the training data. And so what I'm pointing to then is this kind of middle ground where we make use of existing stats, physics, and mathematics knowledge, and then we also acknowledge there are parts of the reconstruction algorithm that we don't quite know what they should be like, and so we can begin to use training data to fill in the gaps, if you like, in our knowledge. Okay, so a very quick review of state-of-the-art reconstruction. In other words, that top end of the slide that I've been showing before. We've come all the way from filtered back projection, in other words, inversion of the radon transform, through to using Poisson log likelihoods, where we improve the statistical model of the data, and that's MLEM, OSEM, and you can see we get a noise reduction there. And then with improving modeling of the physics, such as positron range, hence Dirac mentioned there, we can see that we can, to some extent, recover lost resolution. And then more recently, with the push to lower dose imaging or shorter scan times, we can end up back with noisy images again. And so this is just a post-smoothed MLEM. But we can use quite sophisticated regularization strategies, quadratic priors, not that sophisticated, but then MR guidance comes in. And you can see that with just our claims of knowing what we're doing, we can end up with fairly good images, but there are definitely issues here, as I'll point out on the next slide. So what are the issues? In other words, why even use deep learning in the context of reconstruction? Well, first of all, those conventional reconstruction methods are fitting images to noisy data, hence the need to regularize. And when we regularize, we're either using something that's mathematically convenient and simple, total variation, quadratic priors, or we're beginning to build in, for example, MR information. And the point is that we are claiming we know how to regularize, how to compensate for noise. And hopefully you'd agree with me that we can't really make such claims. And also in those methods, we are assuming that we know the system model, the mapping from an image to the data. We're assuming we know the noise distribution. And as mentioned, we're assuming we know how to regularize. So conventional methods, state-of-the-art ones, are making a whole range of assumptions. And of course, the point I'm making is, do we really know all of those things as well as we claim that we seem to claim that we do know. And so this is where deep learning comes in, where as I've mentioned many times now, we're going to be using real data examples to fill in the gaps in our knowledge. And in fact, we can push it to the bottom end of that slide in the previous slide, where we end up learning the whole of the mapping, kind of inverting the forward model and so on. But really the one I want to point to more in this presentation is the example of learning how to regularize images. In other words, just using deep learning for that part of the process and leaning on our models for the rest. Okay, so what would that look like? This is a simple analogy here. We can consider an image, here's an MR image of course, as a collection of pixels. In other words, that's just a point in a very high dimensional vector space. And so we could imagine all conceivable MR images sitting in some what we call manifold, some kind of region of a high dimensional vector space, whereas natural images might occupy another manifold in the same vector space if this was the same size as that image. And likewise, PET images sit in another manifold. In other words, all the high quality PET images of FDG, for example, we could assume sit in a particular region in a high dimensional vector space, such that when we've got a very low count scan, what we're going to be saying is in our reconstruction, well, we expect that reconstruction to actually sit somewhere within the manifold of high quality FDG PET reconstructions. So that's what we're going to be doing in regularization, is kind of just really trying to encourage our reconstruction to be in the manifold of our training set. Okay, so here's an overview slide of the kind of ways that we can build deep learning into PET reconstruction. I've got hours of content on all of this, and I can really only touch on a couple of examples today. So I'm going to go through the top one and the third one here, but just to say the one here, this second one is really, you've seen it very briefly earlier. That's that deep PET architecture, completely data-driven, uses huge quantities of training data, works brilliantly when you test it within distribution, but is maybe questionable when you go outside distribution. But anyway, I'll focus on 1 and 3. And the one that I won't talk about, other than just briefly now, is deep learned representations like deep image prior, where in fact you don't even need any training data at all. And that's just really in the spirit of just learning what the code is, even just for the data that you have in hand. Anyway, let's move on to post-reconstruction methods, and then we'll talk about unrolled iterative reconstruction. So post-reconstruction, this is going to be kind of largely data-driven. It's just taking post-reconstructed images and then mapping them to high-quality examples. This is a very simple example. I think you may have seen it before, but I really like this work by Georg Schramm, so that's why I'm mentioning it here. Very easy to understand. Just use lots of example data sets where you have the standard OSEM reconstruction, and then hopefully you've got a registered T1 weighted MR as well. And then what the training set has is these standard reconstructions, and then also the high quality MapEM anatomically guided PET reconstruction. You can see that's a nice reconstructed image. And so this simple use of deep learning is basically trying to learn the code or the mapping that will take you from your vanilla standard OSEM all the way through to a high quality state-of-the-art PET reconstruction. And so it really is just what we've been seeing before. It's basically learning a lot of convolutional mappings. These are 3x3x3 convolution kernels. And here there'll just be 15 of those, single channel. And then as we go along, we end up having to use multi-channel kernels in order to basically convolve multiple input feature maps as we progress through this cascade of convolutional operators. And of course, we've got nonlinearities in there. And furthermore, in this particular architecture, what they're saying is to basically learn what is the difference between the OSEM reconstruction and the high quality output. So given this input and this MR, we just go through and learn all the different features that we need in order to generate the difference image that can be added to that to generate the high quality output. And so here in this cascade of convolutional operators, basically 170,000 parameters were learned, only using 26 training data sets from 2 tracers, 2 scanners, and simply looking at the agreement between the predicted output and the actual high quality reference, just by looking at mean square error loss and then using good old backpropagation in training to update the parameters of this deep network. So very nice work published in Neuromage 2021. just to show here that if you did a conventional MapEM reconstruction to get that, normally you'd be dealing with maybe 100+ minutes of processing time. If you run it through a CNN on a GPU, we could be down to 1 second. So here are the test time results for that. And the reason I'm showing this example is because this is actually working very nicely outside the training distribution. This is a tracer F18 FET that was not within the training set. And yet by learning this mapping, you can see the prediction here visually agrees very well indeed with the actual MapEM reconstruction. Okay, so that was just learning, really learning from data examples, how to get from an input to an output. So this is a kind of little cartoon that I did with Gail Schramm in a recent Hot Topic article, which it can be seen as kind of just picking up a book on mindless nonlinear algebra and throwing away the physics. That's what a skeptic could say. But those of us that are fans of AI really do see it as this kind of nice hybrid kind of compromise between our knowledge, our problem, and then using machine or deep learning to come in and help fill in the gaps. And it's kind of this two-way conversational balance between modeling and using the data. And that's the article I'm referring to with this kind of cartoon in it. And so that's where unrolled iterative reconstruction with deep learning would fit in, is this kind of balance between those two extremes. So we've got mathematics, we've got statistics, and we've got data all going in. And again, this is clearly the direction that I see us going in the longer term. So this is a very well-known algorithm. Most of you are familiar with it, ordered subsets at EM. It's just a very simple forward projection, ratio, back project, multiply. And that is, of course, none other than just a cascade of programming operations. In other words, it's a deep network where each of these blocks is just a repetition of that algorithm. And with noisy data, when you put in start off with a uniform initial image, and when you put in noisy data, you get potentially a very noisy output reconstruction. And of course, it was one of the godfathers of deep learning, Yann LeCun, in fact, who was behind this kind of approach of unrolling iterative methods, even as far back as 2010. Just a quick aside. Anyway, so conventionally, these methods, the MLEM method, would be regularized by MapEM, and that's what I've been talking about before with those regularized methods. And so just to show that even a regularized MapEM method is, again, just a cascade of operations. It's just a deep network where we are hardwiring what those programming steps need to be. And so what does a MapEM update look like? Well, one way of looking at it for the particular algorithm that I use a lot would be to say, well, it's just that conventional MLEM update fused or joined together with a simple denoising of the current image. And so if you go through that process, you can end up with these regularized reconstructions. But the point is, this construct is based on our mathematically convenient quadratic prior, very unlikely to be optimal. And as talked about before, that can often be upgraded by putting in MR information to guide and control that denoising step. And we end up with an MR guided reconstruction built on all of our assumptions about how things should be done in that programming sequence. And so again, the constant message I'm putting across here is this also is unlikely to be optimal. We've made all kinds of assumptions about how much to regularize, how much anatomical MR information to put in there. And so hence the need to learn from data examples to learn how to best make use of MR, how to best regularize. And so that is what is behind then FBSSCM-Net, a method I worked on a while back, where we take this construct of the standard sequence of coding lines taking us from an initial image to the output image with this block here, and we just replace it with a component that we learn from example data. So we take an image here, instead of just naively doing a simple mathematically motivated denoising step based on a quadratic prior or MR guidance, instead we learn a convolutional neural network which will appropriately denoise this such that when it's fused with the data fidelity EM update, we get an output which by the end of the sequence will give something that corresponds to a reconstruction from higher quality data. So this then needs to be trained, and we do it by using target or reference or label data where, for example, this could be a higher count acquisition. So this is just an illustration here, 30 minutes of data as opposed to 2 minutes of data. If we considered 30 minutes as rich enough data, then we wouldn't need to regularize. We could just do regular MLEM, get a reconstructed image, and then we just require that if we only had a fraction of the data, as in this top line here, we require this CNN to appropriately denoise, in other words, to kind of put that image onto the high quality manifold that I talked about before, such that the output here agrees with the high quality data output. And we use typically, mean square error is just one example. There are many examples of loss functions that can be used. And so we just look at that loss function, and based on that, we can update the parameters via the training process of backpropagation of gradients of this loss function with respect to the parameters of the neural network. Okay, so what I'm talking about here then is a mapping, a sequence of coding steps that are making use of our modeling knowledge, the system matrix for the scanner, the Poisson distribution, but then also using data to fill in the gaps for the regularization part that we can't really claim to know very well. So here it is in practice. This is just that FBSSCM-Net, which is a kind of a realization of that methodology I've just been talking about. So we've got a CNN and an EM update fused together, and then we just iterate to deliver a high quality output. And here we're training up just 77,000 parameters for all of the various convolution kernels in the CNN, and using 35 training pairs to fill in the missing information in terms of the parameters for that CNN. These are the kind of results that are obtained with that, and they're obviously visually quite impressive. This is the high quality reference in this column, 30 minutes, compared to just the lower count data of 2 minutes for OSEM. And this also only used 2 minutes of data, but it used the CNN that had been trained by the high quality examples to deliver notable improvements compared to OSEM. Okay, and there have been recent variations on this. We published a more practical 3D sequential training process for this, because this can be a very large network with a lot of feature maps, and so challenging for GPU memory. So we looked at sequential training. That was published in 2021, and others have really picked up on this approach as well, and even used transformer-based architectures instead of a CNN to try and deliver further improvements. And I still feel that there's a lot of work there to be done for transformer-based architectures. So in summary, for the Unrolled kind of approach to reconstruction, we're using known physics, stats, and mathematics, our trusted algorithms. And what we're doing is using training data to learn how to regularize. That way, we don't need so many training pairs. In other words, maybe 35 were working well for the example I've just talked about. We expect improved generalization as a result of using our models in tandem with data, and this is a practical method for 3D reconstruction, although it is slower than just, for example, the CNN I showed earlier for Georg Schramm's work. That is actually lightning fast, about a second or so to do a prediction. But here we're doing our conventional programming as well, and so we're back to slower reconstruction times. And here are just some example methods in that category. Right, in the closing minutes, I'll just touch on some recent research directions. First then, to start with joint PET-MR reconstruction, I'll go through this quite quickly. Just to say, the motivation for joint PET-MR reconstruction is to exploit similar information between modalities in order to deliver what we call a synergistic outcome. In other words, doing better than if we had reconstructed PET and reconstructed MR separately. So we're trying to make use of common information and yet avoid misguidance that could happen where there are differences between the PET and the MR. So just to show you the kind of architecture that we've been working on, we'd have what I've talked you through before. We'd have the PET reconstruction as this cascade of operations on that top rail. And then on the bottom, we'd do the same for the MR reconstruction. So what does this PET-MR module look like? There's a whole sequence of these, 60 of them. That module is basically composed of an EM update step. And then we have this miniature UNet, a simple CNN, to regularize from the PET and MR information to deliver some output that can be fused with the MR update and also fused with the PET update to deliver a regularized PET and a regularized MR reconstruction. And of course, we're now training to match high quality PET data and fully sampled MR data. This is a zoom in on that UNet. So for 2D simulation examples, it's just 58,000 parameters, 200 training pairs. For 3D, 160,000 parameters, 18 training pairs. And it's just basically a convolutional neural network with downsampling and upsampling. Again, could talk about UNets another time, and you're probably already familiar with them. These are the kind of results for just the humble simulated data. We've got real data results. We're hoping to publish those imminently. I'm just showing you the simulation examples here. So if we look at conventional methods here, MR-guided reconstructions are delivering the lowest kind of global error in a reconstruction of this FDG brain simulation. If we go to deep learning methods, like I've just talked you through before, where we only do one modality, in other words, just do the PET by itself, but then feed in MR guidance information without reconstructing the MR, then we get this notable improvement along the lines of what we've seen before. But there is this modality unique, in other words, PET unique lesion that is at risk and clearly is being lost here if we are not careful with how we go about using our MR guidance information. And just to say, the joint method that I've briefly touched on is able to try and deliver a nice compromise where we get the modality unique information along with the benefits of common information between both modalities. And then just to finish within my closing minute, if I've even got that, we're also currently working, these are kind of old results, I'm not showing you my very, very latest, that will come out soon, where we've been working on using deep learning to separate out dual tracer or multiplexed imaging, where we're trying to put in two traces at the same time and separate out the two signals. And of course we can use deep learning to do that. So this is FDG and methionine injected, not quite simultaneously, but together in the field of view at the same time. And then we just put that into a convolutional encoder and then two different decoders to predict what the separated FDG and the separated methionine would look like from this dual tracer multiplexed input dynamic sequence. And long story short is that deep learning does surprisingly well in being able to predict what the separate scans would have been, or to infer what the underlying data are from each of the traces. So we get a good inference for the FDG and for the methionine with acceptably low errors. So the emphasis I've been drawing out here is that we need a balance between our claims of modeling the whole lot, where we claim we know what we're doing, through to the claim that we know nothing and just use data. We need to sit in the middle somewhere on that spectrum. I haven't really talked a lot about modular deep learning. And obviously, I'm stating here deep learning can be used to improve image quality. You'll probably see that much later on today. We need to assess this for various clinical tasks, and uncertainty quantification needs to be looked at, and also better deep learning architectures like transformers with integrated multimodal data will be an exciting way forward. So I'll stop there. Thank you very much for the time allocation.